Good morning, everybody. Thanks for joining us again for another edition of the Building Smart Energy Efficiency Essentials for Modern Home series. Today, we're talking about one of my favorite topics, passive house certification and net zero homes. As is typically the case, we're going to go ahead and give it just a quick minute for all the other participants to arrive. So just hang tight and we will get going here soon. Okay, we're going to go ahead and rock and roll. Thank you again to everybody who is here in attendance. We are in the home stretch of our webinar series. We've been doing these basically almost every week since May. We've got crisp fall weather out there. My heating system is starting to run. But you know what? If I lived in a passive house, which in many ways I wish that I did. I love my home, but I live in a renovated 1927 era home in Detroit. Do not live in a passive home. But if I did, there's a good chance that my heat wouldn't have even turned on yet this year. And you may be going, I don't believe you. I don't believe that that's possible. It's been cold, Chris. It's been like down in the 30s. Yeah, you're right. But the thing with passive house is it's almost like magic. You add the right amount of insulation and you make the house ultra airtight, and you are thoughtful about introducing some positive solar gains into the building. And it's like the building basically sustains itself practically without any heat. Now, obviously, passive house, it does actually have active heating systems. But this is why it's one of my favorite topics and why I'm so excited to present to you here on this edition of the Efficiency Essentials for Modern Home series by DTE and Consumers Energy, because passive house really is very special. It really is a method to have homes that almost entirely squash heating loads. And it gives us a great way to go from a energy efficient home to a net zero home and to actually achieve that. So diving into the presentation today, what is passive house and what's net zero for that matter? I think people have some misconceptions about what these programs are, what they mean, what they don't mean. What are any relevant certification programs, related to these programs? What are kind of the key design principles that separate passive buildings from other types of buildings? And then how can we get all the way to net zero? So again, I'm Chris McTaggart, president of Building Efficiency Resources based here in Detroit, Michigan. I'm a hometown, home state kind of guy. I love the state of Michigan. Our company works with home energy raters all around the country, several throughout the state of Michigan, and I'm very passionate about high performance buildings based here in Michigan. I'm uniquely qualified in order to present on Passive House because I have been an instructor for the Passive House Institute US since 2014. So I've been involved with Passive House now for well over a decade. And so I really do understand the principles and the science behind all of this. So jumping right into it, if we start with kind of the principles of energy efficiency versus conservation. So, conservation is going without, putting the sweatshirt on in the middle of winter instead of running the heat to a decent temperature, versus energy efficiency is just having a product or a system that uses less without needing to do without. Both will reduce in or result in energy savings or greenhouse gas emissions. But the goal with passive house is we don't want to go without. We want to have low energy buildings, but we don't want to go without having comfort in our buildings. We don't want to go without having, the quality of life that we would expect. So first and foremost, just to dispel any myths, passive house is not asking people to change their lifestyle. It's not asking you to conserve more energy through choices. What it is doing is it is attempting to squash our loads, and in particular, our heating loads, so as to have a low energy building, one that consumes, 60% or less total energy, and probably 80% or more less energy compared to like a standard code built home built to the 2009 IUCC, which, if you've been following us since the beginning of this series, Michigan's energy code as it currently published may say 2015 IUCC, but it's actually a lot closer to the 2009 in terms of actual performance. So the goal here is for our annualized energy, as well as our peaks, to be substantially lower with passive buildings, which not only allows for people to be more comfortable, but also allows their bills to potentially be very controlled, as well as possibly offset by on-site renewable energy to become a net zero building. So, if we take a look at the goals of passive house, so, step one is a deep energy efficiency. So let's go ahead and, again, squash our total energy consumption by 60% or maybe even more compared to a baseline building. And then go ahead and add renewable energy in order to get all the way to net zero. Now, you do not have to be a net zero building in order to be passive house. It just so happens to be that when you build to passive house, you're really setting yourself up so that it's a lot easier to get there should someone desire to achieve net zero. I happen to have been the passive house rater on 3 FIAS certified ratings. Actually, the first one in Michigan, built in the Ann Arbor area, and the second one built in the Ann Arbor area, and recently a third one built in Birmingham. The first 2 were not net zero. They were passive. They did include some on-site renewable energy, but not enough in order to get all the way to net zero. They just chose to not basically add that big of a system. Whereas the last one, not only did it achieve passive house, but it achieved what's called FIAS zero, which is getting all the way to net zero. And they even had enough on-site renewables left over to power electric vehicles on site. So pretty cool stuff there. So again, energy conservation, we'll call that, with the building envelope, basically, we're not wrapping our bodies in a sweater, but we're wrapping the house in a nice airtight, well-insulated cushion so that we're reducing our loads. By reducing our loads, that means that our appliances, our heating, cooling, HVAC systems have to work less hard in order to keep us comfortable. So that's why, we kind of start off with this idea of just how do we reduce the need for energy, in particular the heating energy demand. And then we put in best-in-class appliances and HVAC and water heating systems so that the building is operating very energy efficiently. And then finally, we can go ahead and add renewables such as solar PV or wind power or something else possibly as the final measure. That's the goal of Passive House. Again, you do not have to add on-site renewable energy to be a passive house. It just so happens to be that these techniques lend themselves to getting all the way to zero. So here's kind of how this all works is so, if we talk about the HERS reference home, that's based off the 2006 IECC. And then, 2009, that HERS reference home scores a 100 on the HERS index. 2009 is somewhere around 80s or 90s. 2012 is somewhere in the sort of 50 to 80 range. Energy Star version 3.2 definitely is going to get you probably, and the 30s or 40s. I don't know about that. That's a little bit exceptional, but you might be somewhere in the 50s for Energy Star. Indoor Air Plus gives you a better indoor air quality product. We can go all the way to zero energy ready homes. That's soundly in the 40s for version 2 for sure. And then we get into FIAS Core, and somewhere in the 30s to 40s on the index is where you're going to be for FIAS, just the standard FIAS. There is and FIAS stands for the Passive House Institute US. There is another passive house labeling program called Passive House International, or PHI. And I don't want to say which one's better. Obviously, I've worked with FIAS. I think FIAS plays nicer with a lot of the HERS system and the federal programs that we're all used to. So I think that it's more adapted to our country and our built environment. Anyways, and then the last step would be go all the way to FIAS Zero, or I believe PHI also has a commensurate zero energy program as well. So that would be kind of the next stepping stone, would be let's go all the way to zero. So to be clear, especially if you're doing FIAS, part of being FIAS is that you have to certify to zero energy ready homes, Indoor Air Plus, and Energy Star in order to be compliant with FIAS. Okay, so here's a little bit of a timeline of where did this idea even come from. So basically, the high performance super insulated buildings go all the way back to the 1970s in North America. There was a prescription that was put together called the Illinois Low-Cal House, put together by the University of Illinois in Champaign-Urbana, where they created basically these templates for super insulated buildings with things like balanced heat recovery ventilation. This goes all the way back to the 1970s. Triple pane windows, airtight construction. Before we even had blower doors, they knew that conserving, making our house more airtight was going to conserve energy. They knew that adding more insulation would help us basically reduce the need for heating. So this stuff goes back a long time. There were different Canadian as well as US examples in the 1970s and 80s about, how do we drop the heating load to 15% of a typical heating load, and then use things like solar thermal in order to heat the building. Now, I would say some of those early concepts created potentially the risk of overheating because they became very solar dominated buildings. So it's important to understand with passive house, while it uses the free energy from the sun as part of a way to reduce our heating loads, it is not intended to be a passive solar program, meaning that you're not just trying to get more and more and more free solar gain through windows in order to heat buildings. Because the problem is that even in the swing seasons, or possibly even in the dead of winter, if you make a house so well buttoned up and so well insulated, and then you're bringing in more and more and more unshaded south-facing glazing, you can overheat buildings even in the dead of winter, and you make people very uncomfortable. And then you've got right like today's a high 50s day in Detroit. If I had way too much south-facing glazing that was unshielded, I might even be tempted to run my air conditioning. I've seen this before. with Passive House, where people basically go a little bit too overboard with their passive solar elements at the expense of some of the other elements of the building. So in 1996, PHI, Passive House Institute, International, was based in Germany. They set the original targets for what a passive house would be. And then in 2002, a German born and trained architect, Katrine Klingenberg, created the first certified passive house in North America, based actually in Urbana, Illinois, ironically enough. She was there living with her husband, and they decided to build a passive house. And then FIAS was actually formed in 2007 in order to be a separate certification body focused on North America. And since 2015, FIAS has focused on creating basically a North American standard, a climate-specific standard. And the reason why is that the German standard was very, and still is today, very focused on heating-dominated climates that have pretty low humidity and really not very extreme temperatures. So think about, if you've never been to Central Europe, Germany, it really is pretty moderate. It's kind of like New England in some ways in terms of its climate. It's pretty moderate. Yes, there are alpine regions with the Alps that where it gets colder and snowier, but that's not typical. That's not most of Germany. So the PHI standard was really sort of tailored to think about the Pacific Northwest or the Northeast. It really wasn't factoring in things like swampy, hot and humid summers like we get in the upper Midwest, or extreme cold. It doesn't in Central Europe usually drop down to 0 degrees Fahrenheit or anywhere near that, or even below that, pretty much almost ever. So the PHI standard was really kind of focused on that climate and how to really execute high performance with Central Europe. North America has extremes. We have extreme hot and humid. We have extreme hot and sunny. We have extreme very cold. And then we have mixed climates like, Chicago and Detroit and places like that, that we kind of, in some ways, we get the worst of all worlds. We get, hot and humid summers, and we get cold, pretty darn cold winters. So for that reason, FIAS decided that it needed to create a more cost optimized standard that focused on the various North American climates. So that gives you a little bit about the timeline. Let's jump into these programs. So again, we've already teased this. There are two different passive certification bodies: PHI, Passive House Institute, and FIAS. And here's their sort of mission statements. And again, PHI does have a footprint in North America. There are actually the first certified passive house in Michigan, to my knowledge, was a PHI certified building, I believe somewhere in North Oakland County. There's been PHI buildings on Beaver Island, out in Lake Michigan. So PHI does have a footprint in the state of Michigan. They do have certification standards that are intending to certify buildings in Michigan and any other state, basically, as well as Canada. And I would say that FIAS is picked up more momentum because it's the Passive House Institute US. Again, they created more of a climate-specific standard that was intended to focus on US or North American-based various climates that we have, so as to create a cost-optimized approach. Again, the PHI standard is really obsessed with quashing heating loads. So comparatively, PHI, if we just had to make generalizations, PHI homes tend to have even more insulation required than FIAS in order to be certified. And some people think that's great. It's a German standard. It's very robust in its engineering. But, and again, I don't want to say these are bad homes. I think PHI homes are great homes. But there's potentially the risk of overdoing it in terms of expense on insulation, maybe not focusing on the more holistic elements of the building as FIAS has tried to. FIAS is really trying to hit that sweet spot in terms of compliance where, yes, the building is very airtight. Yes, the building is very well insulated. Yes, it factors in some positive solar gains and interior gains, but it's not just trying to overheat the building in order to save energy. So both of these programs have sort of various sub-brands. FIAS is pretty nimble insofar as they really only have two major brands. They do have a Revive standard that's intended for retrofits, but I'll say it's still in development. So really, you can be FIAS Core and you can be FIAS Zero. And zero basically means that you met the passive standard, and then you've added enough sufficient on-site renewable energy to be considered to be a zero energy building. PHI has a label both for sort of standard construction as well as for renovations. That's the EnerFit standard. Then they have a low energy building, which is sort of like not quite passive house, but kind of better than normal. And then they've got a label for a retrofit plan. So basically certifying the plan to renovate the building. Both organizations also certify products. So they certify the whole building, but they will also certify products. In particular, window systems will be certified by the manufacturers, or so not by the manufacturers. They will be certified by the programs. Also, like energy recovery and heat recovery ventilators are able to be certified. Prefabricated building systems, like prefabricated walls, can also be certified by FIAS or PHI. In terms of the professionals involved, PHI has a certified designer, and that would be equivalent to the FIAS consultant. So in the FIAS world, we call them the Certified Passive House Consultant, CPHC. In PHI, they would call them the CPHD, Certified Designer. Kind of the same approach, but these are the people who are maybe doing the focused energy modeling, because for these programs, you have to do more than just HERS modeling. You have to do a more bespoke, focused energy model. We'll get into what that modeling looks like here in a minute, but basically, this passive house designer / consultant is considered to be the building science guru of the project. They're helping to design the building systems and assemblies to meet the passive house standard, and then use the energy modeling tools to document that. PHI has a certified tradesperson that would be similar to FIAS's certified builder. And so what you'll notice here is that PHI does not have a certification for a rater or verifier. FIAS does. So FIAS has tied itself into our North American verification system to recognize the value of third-party verification. So HERS raters can earn, through training and examination, the ability to be recognized as FIAS certified raters, focus really on low-rise, single-family, duplex, townhouse-style buildings, whereas verifiers are also typically HERS raters, but they're more focused on either multifamily construction or on non-residential. And I'll just say that the application of passive building has really shifted from focusing on houses to focusing in particular on multifamily construction. So there's a lot of focus on verification of passive multifamily, particularly in places like the Northeast of the United States. In terms of software, again, I mentioned that HERS modeling is not good enough for passive certification. Under PHI, they use essentially a spreadsheet-based software tool called the Passive House Planning Package, or PHPP. And it's a worksheet workbook in Excel that calculates very specific values for heating demand, peak loads, primary energy, which is otherwise known as source energy. That's basically taking all all the energy that a house uses on an annual basis and then multiplying it by grid source factors. So, like, I don't know if you knew this or not, but for electricity, our grid source factor in the US is about 3 to 1. So if you use, we'll just say, 100,000 kilowatt hours per year in order to run your house, that's site energy. The actual power plant based energy consumed would be about 3 times as much. So it'd be 300,000 kilowatt hours per year. Again, in the passive world, we're not just focused on what's going on at the house, but also what's happening at the grid level. And then you'll see that there's also a specific line item for air tightness. Now, you may be looking at this and say, I don't really understand what these things are saying. This is all a metric. That's right, because it is a German-based standard. Now, I believe that they have a version that is in the inch-pound imperial system that you can use. But otherwise, yeah, in the world of passive house, you probably need to get familiar with some conversions to metric for some calculations. For FIAS uses a program called Woofy software. And there's both a desktop version as well as now there is an online version that is able to be accessed. Similar kind of a deal. You basically draw the building out, typically in SketchUp, and then import it into the software. And by importing it into the software, it basically gives a 3D representation of the building, which can be used especially for predicting solar gains and any possible shading that occurs. Because things like window shading are a big deal in the world of passive house. It's a big deal to take advantage of solar gain, but to also block it out when it's not advantageous. So Woofy is it's a little bit more complex in terms of how you enter in things like building assemblies. The way that mechanicals are entered, it's a little bit less traditional than like what we use with Ecotrope or RemRate, where you're looking up model numbers in AHRI and entering in the data. It's a little bit different. There's a lot of sort of calculators and protocols for kind of roughing some of these things into the software. But same kind of deal. Ultimately, the annual heating load and cooling load are those are bars of compliance, as well as heating demand and cooling demand. Those are our peak loads. And then source energy, same deal. There's a source energy target. And there is also a very stringent air tightness requirement. So what you'll notice about like this colorful graph here is out of the energy puzzle for this house, space heating is amongst one of the smallest bars for this house. And this is a house built in Chicago. So it's pretty incredible. This particular building that we're seeing here in Chicago, basically space heating consumes just a little bit more energy than lighting does. Your standard, cooking and refrigeration and clothes washing appliances actually consume almost 3 times as much energy as space heating in Chicago. Water heating consumes way more energy. So it just goes to show that, in the world of passive house, really sipping space heating energy is a big part of the process. That is a big goal of passive house and a big way that we're able to have low energy buildings. This is sort of how PHI looks at its certification criteria. Again, there's a trade-off. You can certify either under annual heating and cooling, so that'd be like the total amount of energy used for heating and cooling throughout the course of an entire year, or you could trade it off and look at it just at peak loads. Let's take a look at these peak loads. So let's imagine we've got a 2,000 square foot building So that'd be 2,000 times 3.17 gives you just over a half ton, excuse me, just over a half ton of heating. That's your peak load. Now, it's calculated differently than our manual J loads. It's like a seasonal average, like a cold month, kind of the average temperature. So you wouldn't necessarily want to size your equipment based off of it, but still very, very low energy for heating and cooling. Primary energy, it's a little bit hard to conceptualize what this means, but basically it's just a very low amount of energy used on an annual basis per square foot. And then for air tightness, the goal is basically 0.6 ACH50 or less for air tightness. The goal here of passive building is kind of like, can we have it really well insulated? You know, again, below that red line is those are requirements for how to get there. Can we get an R40 envelope all the way around with R50, you know, UFIT 0.15 windows all the way around with high solar heat gain coefficient? And then if we do that, basically because we're so darn airtight and so well insulated with low thermal bridges, we barely need to even heat the building. We can just heat it with the sun and maybe just add in a small amount of supplemental heat along with our balanced ventilation. That's the goal of Passive House. Now, FIAS is so continuing on with PHI. You know, again, you know, there is some modifications that have come into the system over time that allow for some additional allowances, like cooling is now not just cooling, but it's cooling plus dehumidification. You know, and so there's some, I'd say, modifications that have occurred over time, but that's pretty much what PHI is about. Again, you can certify classic, plus, or a premium, and it's that basically that's the amount of renewables that are allowed per each of these design packages. Again, you know, it's not to diminish PHI, but FIAS just works a lot closer to what we're used to in the United States. It's optimized for our climates here. It includes our utility grid source energy factors. It kind of takes advantage of the North American third-party verification system through raters and verifiers. So there's a lot to be said about the FIAS approach. Again, they've tried to really make a sweet spot in terms of the climate values that you would needed for like insulation and whatnot. They're trying to get you to have a building that is robust but not overkill. So here we go. We got Flint, Michigan, and so this would be our if we were going to follow the prescriptive approach. So FIAS allows you to actually do a non-modeling approach for houses called the prescriptive approach. And so if we take a look at this, like our windows would be 0.15. Those are pretty good windows. A 0.82 sensible recovery efficiency for either our ERV or HRV. Our walls would be R40, our roof would be R70, our floor would be R30, and our foundation walls would be about R20. And then we need to have sort of a at 5-degree COP of our air source heat pump of 1.75 and a minimum SEER of 15. So this would be if we were going to follow the prescriptive approach. If you go the modeling approach, you don't have to hit these precise values. You may be looking at this and going, wow, this is quite a bit. And you're right, it's quite a bit more than standard. Like I'd say below grade walls being about an R20, that's really not that big of a deal. You know, the standard modern energy codes require R15 continuous. So, you know, we're just adding about an extra inch of insulation on the below grade walls. You know, the roof going up to an R72, yeah, that sounds like a lot, but compared to R49, we're not talking about really all that much more, you know, just a few more inches of insulation. Floors being an R30, big deal. That's not a big deal. You know, the walls and the windows, I think, are the bigger deal, right? Where we've got R40 walls and you know, 0.15 windows. That means you're getting some really good triple pane windows and you're getting, you know, a more robust wall package. I'd say that's very not standard for the way we look at things in the typical construction world. But if you think about it this way, our above grade walls tend to be our largest surface area in our house. We also tend to live closer to them. So, like right now, I'm 4 feet away from my walls and windows, and it's a little bit cool outside, and so there's a little bit of a comfort issue just sitting here. It feels a little bit cool in this room because I'm so close to these getting cooler walls. And as we should know as building scientists, heat goes from hot to cold, and radiation is the primary form of heat transfer. So me sitting in, close to my walls here, there's actually heat being sucked off my body and going to these walls. So if we go and have higher performance walls and windows, yeah, it's going to add some complexity and some cost to the construction, but man, it's really going to make it a nice and cozy building. That's for sure. FIAS does require co-requisite certification under what was Zero Energy Ready Homes. Now it's the DOE Efficient Building Program, Energy Star, and then Indoor Air Plus. PHI, the steps to certification are a initial design review, and then submission of a lot of photos through construction. There is no third-party verification requirement. There is no requirement to have a rater or another approved third party go out. So like literally the builder can self-certify. That's quite a bit different than the way we approach things in the FIAS world. The way that FIAS works is that the FIAS consultant, the CPHC, is working with the organization, doing the energy model, getting it approved at pre-certification, and then a rater or verifier, depending on the size and scope of the building, are going out at midpoint and performing on-site verification, testing, and verification to document that the building met all the requirements of the program. And there's a lot of them because not only do you have to be FIAS, but you have to be DOE and Indoor Plus and Energy Star. So there's a lot of devil in the details requirements that have to be met. I will say it's really cool that Consumers Energy this year had a pilot going. You have to have already signed up for it, and you have to have finished by the end of the year. So if anybody got in on this by being either PHI or FIAS, you could have gotten an incentive of $20,000 from consumers. So good on consumers for that. And if it was eligible for the federal tax credit, you could have also gotten $5,000 because it would also be a DOE certified building as well. So up to $25,000 in incentives. Design principles. So, we've talked about kind of how the sausage gets made in terms of the certification standards and the differentiation between them. Now let's talk about some of the design principles. So, and this doesn't really matter whether or not we're talking about FIAS or PHI. They both approach things pretty similarly in terms of principles for design. So the idea is that we're doing what we can in order to then add solar and become a net zero building. The idea is that operating costs are very nominal, and that durability is increased because we've reduced what's called thermal bridging, and we've paid a lot closer attention to the potential of moisture risk and condensation in buildings. And then finally, the goal is that this is a supremely comfortable building. There should be continuous insulation with, it says no thermal bridges. There's no such thing as a thermal bridge free house, but very minimized and then addressed thermal bridging. Airtight construction, extremely airtight. PHI requires 0.6 ACH50. FIAS requires 0.06 CFM50 per enclosure area, which, long story short, for the average house will equal out to about 1 ACH50. So, in that regard, PHI tends to be a little bit more stringent, except when you get to bigger buildings, like tall multifamily buildings, it actually flips. And it turns out that under those big buildings, the 0.6 tends to be more permissive, whereas the FIAS standard tends to be tighter. Again, I mentioned solar gains are part of the passive house sort of magic. The idea is that you get useful gains that can come into your house and you can maintain them at the time of year that they're useful. But then otherwise, you block them out. So, like right now, my house is not very well oriented for solar gain. I have some south facing windows, but only a couple of them really take on any type of direct gain. And so for that reason, my cooling bills tend to be low because I don't have a whole lot of sun beating down through my windows, but I'm also not getting a lot of free heating to offset my heating energy use. So you know, there's pros and cons I can just say, but the goal is to optimize solar gain. Yes, let's bring in a little bit more from south facing windows if possible. Let's limit north facing windows because north facing windows are losers. You don't ever see the sun on the north side, and so there is no useful gain that comes through them. There's just loss. And then on the east and west, let's make sure that we're getting some useful gain, but that it's not overheating the building, especially at the end of the day, if we've got a lot of west facing glazing, there's a risk of overheating the building at the end of the day. And typically, almost always, passive buildings have balanced heat recovery or energy recovery ventilators so that there's exceptional air quality in the buildings. And that because we've done all this great work with continuous insulation, airtight construction, and optimizing our windows, we tend to have a smaller mechanical heating and cooling system as a result. So focusing on these first two elements, these are the most critical variable. A better building envelope is required for passive house. And yes, FIAS has tried to sort of massage the numbers to get it to be more close to cost parity, but make no bones about it. In a single family context, you're going to have continuous insulation on your walls. You're going to have higher insulation levels in your attic and on your foundation walls. You'll even have insulation underneath your slab, even if you have a below grade slab. Why? Because we're trying to conserve the heat inside the building. Air tightness, same deal. But the other issue with air tightness is when we add in so much more insulation, there's a risk if we have air leakage in the building that we actually create the grounds for condensation to occur and moisture wetting inside building assemblies. So if we have ultra insulated but leaky buildings, it's actually much more risky from a durability standpoint. So air tightness is paramount not only for comfort and energy savings, but for durability purposes. So let's take a look at this. When we talk about continuous insulation, what are we talking about? Well, yes, we'll have cavity wall insulation, no doubt about that, but you'll also likely have some type of exterior continuous insulation. What we're seeing in the bottom image is we're seeing continuous rock wool, mineral wool insulation. And you'll see it's not just an inch. That looks more like 4 inches or so. Rock wool is about R4 per inch, and so that's an R16 ish continuous insulation. If we have a 2x6 R20 cellulose on the inside, that means we're up to about an R36 or so. And it may not meet the prescriptive approach, but that's probably about what we need to be in the game in terms of a better overall approach to our building enclosure for our walls. You'll also notice in the sort of the two-dimensional animation here that we draw a red line around the whole building. And the whole idea is that you have continuous insulation around the entire thing. And then basically you tie in your airtight layer in conjunction with that thermal boundary. We also make sure that we're keeping ducts and air handlers inside conditioned space because that's a requirement of zero energy ready homes. Reduce thermal bridges. So, thermal bridges are things like, frankly speaking, like our wood framing and our concrete foundations are potential thermal bridges. And so, and especially where those elements meet. So if an interior to exterior wall meets, That would be potentially a thermal bridge if you didn't insulate that properly. So there's a lot more attention to detail when it comes to the connections of the buildings where it's meeting dissimilar surfaces. So roof to wall connections, um, floor to wall, basement to wall, foundation to wall, wall to window, all these elements, we try to make sure that we don't have just like raw edges that are bleeding heat. We want to make sure that those are addressed from a thermal standpoint as well. Again, why so airtight? Why do we need 0.6 or 1 ACH 50 houses? Well, the real reason is when we're adding so much more insulation, if we allow it to be leaky, there's a risk of moisture coming in. I think everybody's seen these graphics before. If you create a 1-inch hole in a sheet of drywall, you end up letting in 30 quarts of water, versus if you seal up the drywall, through diffusion, basically you only have a third of a quart of water. So we talked about this way back in the day when we were talking about airtightness. Airtightness is not just for saving energy, and it's also not just for comfort, but it's also for moisture risk management, not allowing moisture into our building assemblies, not allowing cold air to come in and create condensation surfaces within building assemblies. So really, the airtightness principles of FIAS and PHI really ultimately have more to do with durability than they do with energy purposes by themselves. Optimize windows and solar gain. Almost always in passive house, you're going to see triple pane windows. You might be able to get away with a high performance double pane possibly, but we're really looking at R5 or better windows typically. And generally speaking, it's not just the glass that's better, it's the whole window, including the frame, that tends to be better. And when you enter in this information in the passive house modeling software, they actually separate out the glass performance from the spacer performance from the framing performance, in order to basically isolate how each of them perform in isolation by themselves. Why is that? Well, the reason why is that, like with standard windows, there is the risk of not only are we wasting energy with them, but if you have just like a standard double pane window that's not really addressed the space or the frame, you look at that far left image, and the inside face of the window can be cold. That's down 36, 37 degrees. You're at risk of and the frame is even worse. The frame is down to about 30 degrees on the inside face. And the risk of this is that you actually have condensation on the window itself. That if we have, a really airtight house and we've conserved for moisture, that means that we have the risk of meeting dew point on the surface of these windows. So incrementally, by improving the frame and the glass package, we can make those windows nice and cozy and warm, so we don't risk potentially having a possibility of condensation on them. That is the idea behind these. We want the inside surface of that window to be nice and cozy, so we do not have condensation risk, we do not have comfort risk, and they are saving energy. We also want to look at windows from how much can they give to us from a positive solar gain perspective, as well as blocking out gain. So you can see here that the overhang on this house is designed so as to allow free heating into the home in the wintertime when the sun is lower on the horizon, and then the overhangs are designed to block out solar gain in the summertime where we don't want solar gain. Why? Well, because solar gain in the summertime makes us have to run our air conditioner. So these are a big part of it, focusing on shading of windows and focused on how can we get useful gain through windows. That's a big part of the passive house process that in conventional construction, even Energy Star and the DOE program, we practically ignore these things altogether. Yes, we're supposed to model them in HERS ratings, but there's no like program requirement to consider shading. And personally, I think there should, because honestly, that's a non-mechanical element that basically does a lot of work for us just using basic, physics. Solar heat gain coefficient ends up being a bigger deal. And I will say, in general, having slightly higher solar heat gain coefficients tends to be advantageous, particularly in our climate. Balanced in heat recovery, moisture ventilation. So basically, since we're having such airtight buildings, again, 0.6 ACH50 or about 1 ACH50, you got to have good fresh air. And people can't just open windows, because that would not only defeat the purpose of us having such airtight and well insulated buildings, but it would also potentially allow bad stuff from outside to get in. Yeah, it's great if you live out in the Rocky Mountains and you can let in some fresh mountain air. But if you live in Melvindale, Michigan, you're right up against a big giant fuel refining factory. And you probably don't want to be breathing that stuff in. So we want to block it out and then have filtered ventilation air. So, again, when you have a standard house, maybe you get ventilation, but it's just random. It's natural ventilation. It comes in whenever the house leaks. We don't know where it's coming from, and there's no way to filter it really. With controlled, continuous, or at least timer-based balanced ventilation, you have predictable amounts of outdoor air that are coming into the building in order to basically keep people having better air quality. For this reason, it's not a hard requirement, but it is almost essentially a hard requirement to have balanced heat recovery ventilation within a passive building. I've only seen passive houses without balanced heat recovery ventilation once, and that was in San Francisco. So basically, it is pretty much a requirement, especially in Michigan. If you're in climate zone 6, we know that it is a hard requirement because zero energy ready homes, or rather the DOE efficient building program, now mandates us having balanced heat recovery ventilation in climate zone 6 and above. So if you're clear and above, you got to have it no matter what, but pretty much plan on having it if you're inside of the state of Michigan whatsoever. And again, to minimize a mechanical system, we're going to go ahead and keep our ducts and envelopes inside the building envelope. We're going to have a better sealed and well insulated building, to the point where you practically could heat the entire house with a hair dryer. And I mean that. That's the idea. Hair dryers put out, several thousand BTUs per hour just out of a single hair dryer. And that's kind of about the amount of heat that we use. Now, most people are using heat pumps for this. You could use a lot of different things, but I would say most people are using heat pumps just because you do get better efficiency and they do provide cooling. Okay, so closing the gap, finally. How do we go from passive, how do we go from an average house to a passive house? Well, we crush the heating loads, we reduce the cooling loads, we try to balance the other loads as well. You may be saying, well, wait a second, appliances go up. Why is that? Well, that's because we crushed our heating loads. And that means that, as a percentage basis, these other loads go up as a result. So we crush our heating loads, and then we try to get more efficient in the other elements. Things like heat pump water heaters, possibly things like other hot water distribution features like drain heat recovery. Again, not a hard requirement, but it's an option. For lights and appliances, Energy Star appliances. We're pointing to the DOE efficient building program, LED lighting, and then finally adding renewables on the building. Again, it is not required to have on-site power production in a FIAS building. However, you do have to at least be renewable ready, because that is a requirement of the DOE efficient building program. So, however, there is the option to go to net zero, or at least add on-site renewables as well. It could be community generated, meaning that the community itself invests in a solar farm or wind turbines in order to provide power for a whole community. Or it could be site generated at the home itself with either ground mount or roof mounted solar. That is the goal for how we can potentially get there. We got to be certified first, though. We got to get certified. There's a lot of people who talk about, oh, I built a passive like design. But then, when I actually talk to them about it, I'm like, actually, you skipped a lot of steps. What you did is you just added a little bit of continuous insulation and an ERV, and you said that you're passive. You have to get all the way to certified, folks. There's a lot of devil in the details and a lot of value that come out of full certification in these programs. And once we get to that point, then we can consider doing things like adding on-site renewables in order to get to zero. How that works essentially would be like if we're at a HERS 35, because we're a FIA certified building, you got to get enough on-site renewables to get pretty darn close to zero HERS. And the needs are going to depend on the size of the house and a few other factors, how many bedrooms, the location, etc. But all I can tell you is it's possible. I have worked with homeowners here in the state of Michigan that have gone all the way to net zero, but they've done so using Passive House as the foundation. So we're basically at a stop here for today. We're going to switch gears away from single family homes and talk a little bit about Energy Star and the DOE multifamily programs next week. So I will look forward to seeing you here 1 week from today, and we're getting close to the finish line. We've got 3 more sessions left, folks. So I'm hoping to see everybody for all these sessions going forward. Thank you all. Thanks, Patrick. Great to see you again, buddy. And we'll talk to you next time.